О. Вот. Ну, сегодня у нас выступает Евгений Вадимович Троицкий. Название теорем Майкла о селекциях и условные ожидания на коммутативных со звездочкой алгебрах. На всякий случай скажу то же самое по-английски. Today our speaker is Evgeny Troitsky from Lomonosov Moscow State University. And the title of his talk is Michael Selection Theorem and Conditional Expectations on Commutative C-star Algebras. Пожалуйста, Евгений Вадимович.
Thank you. Thank you for presenting me and for invitation to speak at this seminar. I'll speak English mostly. At least at one place, I expect that I will will pass to Russian. We consider the question of quantization of branched coverings. This is a topological notion. Maybe I'll say immediately what I mean. So this is an open continuous surjection of compact Hausdorff spaces. Y to X with a uniformly bounded cardinality of fiber. For example, let X be the closed interval and Y is something like this. And then the number of preimages or cardinality of fiber is 1 over this part and 2 over the right-hand part. So this is maybe most simple example, which differs from locally trivial case, So what we understand under this beautiful word quantization, what is a the specific sense in today talk. So we wish to reformulate. So this quantization. So we mean to reformulate this notion in terms of C-star algebras. Of course, C-star algebras here are the algebra of continuous functions on X and on Y. And to use this, so this should be formulated in such a way that it can be extended to non-commutative algebras. So this means quantization. so to pass to the non-commutative algebras. Okay, so this this problem was formulated and studied in our paper with Sasha Pavlov. Of a conditional expectation E from Cy to C of X. So this is a linear bimodule projection, idempotent. And also to keep, of course, we understand that something should be said, should be included concerning the number, the cardinality of fibers. So in fact, we ask the following. So it should be of a finite index. So the finite index, not in the sense of Jones, but in sense of Watatani, So not the algebraical of finite index, but the topological of finite index. This means that there exists a constant k such that k e b star b. So this is constant, simply multiplication by number, is more or less than b star b. So maybe it is better to write here our inclusion p star. So okay, so this the existence of such conditional expectation is closely related to the existence of an inner product. So this is more or less the same that if we define the C of X valued inner product, BC is the conditional expectation of B star C. So this inner product introduces Hilbert C-star module structure over C of X on C of Y. So in fact, today we will not speak about this interpretation, but maybe it would be useful to understand that another description is also possible.
Are you expectation is the left inverse of P star, or we are not accepting this one? Well, how does E related to P star?
So,
or it's totally different?
Okay, so Yes. So in fact, we have the following. It is a projection. Okay. So we have here the unit element, and so P star of P star of 1 E is 1. Okay.
Okay, yes.
And then from the bimodal property, we obtain what you asked. Okay.
Okay, thanks. Mhm.
So this K, okay. So for example, if we consider once again our example, then we can assign to the points here the number 1, to points here 1/2, and so this will be some, I don't know. So this will be, say, psi. And this is a discontinuous function on our space Y. But if we have a continuous function, then we can multiply it by f and take the sum over each fiber. So this will be, so the summation will be denoted by sigma. So this will be E of f. And K in this case will be evidently K will be 2 square 4. K is 4, because here for square or not, no, 2. This will be 2. So in fact, if this function f is concentrated here, so it is 1 here and 0 here, then the value will be only 1/2 of this 1. So to make it greater than b star b, we need to multiply it by 2. So k is 2 in this case. A slightly more complicated situation is the following. So once again, we have as here, and then it decreases to 1/4. Here we have 1/4, and then it increases up to 1/2. So we can arrange in this way, and it still will work. But of course, k here will be 4. These two cases are simple ones because the total space can be covered, so can be covered as a surjection of several copies of X. So in the second case, so this will be, we can map 3 copies of X and cover this one, and here it is sufficient to have 2 copies. But we can consider an example which is not of this sort. So we have, once again, we have closed interval, two closed intervals over it, and countably many smaller intervals. So this space cannot be covered by a finite collection as an image of disjoint union of a finite number of base spaces, but nevertheless the same numbers applied to each piece between dashed lines give us a positive so this expectation can be constructed, the positive answer in this case. In fact, we had the following theorem. In the paper. If so y to x is a branched covering if and only if there exists a conditional expectation E cy to corresponding to, so in that sense, as I have explained, so first we consider the the map P star. So Cx is realized inside Cy, and then we can speak about conditional expectations. В этом месте уместно рассказать некоторую историю, которую я по-английски не берусь рассказать. Поэтому небольшой кусочек, который я расскажу по-русски. Я очень люблю эту историю, и, наверное, многие из вас слышали от меня, может, не только от меня, но все равно я повторюсь. Некоторое время назад, давно уже достаточно, когда существовало такое понятие, как высокая печать, то есть производился набор литер, напечатались соответствующие книжки, в том числе научные издания, публиковался некоторый сборник, а может быть, это был том журнала, посвященный какой-то тематике. В общем, это были статьи по дискретной математике. Все было набрано, приготовлено, так сказать, уже почти печатать. И в этот момент выяснилось, что в одной теореме имеется ошибка, она верна при значительно более жестких, только при значительно более жестких условиях. А рассыпать набор было невозможно. Необходимо было, так сказать, сохранить. Единственная возможность была только сделать подстрочное замечание. И, значит, подумав, сделали следующее. Сделали сноску под той теоремой и написали, что теорема верна не всегда. So returning here, I need to say, put here a footnote. And write the theorem is true, not always. Okay, more precisely, in September of the last year, Alexandru Chirvasitu from Buffalo discovered that this theorem is not always true. So more precisely, in the direction from left to right, everything, from right to left, everything is okay. And from the left to right, he detected some problem. So in fact, in two his preprints, electronic preprints, which I mentioned in the announcement of this talk, he proved in particular two following statements. First, if the spaces are metrizable, a compact Hausdorff space is metrizable if and only if it is second countable. So, and since we have only finitely many pre-images, this is the same thing as X or Y is second countable. It is sufficient to ask only one of them. Then this direction is also true. And second, he found a counterexample to above theorem for some, of course, non-metrizable. And also a lot of other small things and generalizations he considered. So, in fact, I wish to explain these two items. So his proof for metrizable spaces and the counterexample. Because his approach seems to me applicable in many situations. It seems to me wider than repairing of our theory. It is maybe it would be useful for the audience in some research. I don't know, but in fact, it seems to me beautiful and somehow industrial, because our proof was a little bit handmade. So it is possible, to my mind, to repair it, but in any case, I think that with more strong restrictions only. So, but so I cannot give at this moment the answer to which extent the old proof can be saved. So I would like to speak about this new and for me more interesting approach. So so this will be related to both items are related to the theory of continuous selections of set-valued maps, so-called Michael's theorem and its generalizations, its different versions. So so first, we wish to interpretate another interpretation of our expectations. We have y over x, and C of x is inside C of y. And for each x, we have a finite fiber. Now, consider some map which sends each x from the base space to some e sub x. This is a state. So if we denote y of x, this fiber, we consider continuous function on it. So this is a finite dimensional complex space, and this is the state space. So this is a state on the algebra of functions on fiber. And this states on a fiber can be considered as a subset of all functionals on the algebra C of y. Because if we have a function, so here sits some f, we can restrict it to y of x, then we will have will be an element here, and then we can apply e of x. So values are really in this C y star. So, and also we will restrict this map to be, of course, star weak continuous. So, I mean, star weak topology will be in this functional space, and on X, that topology which we have, which we had from the very beginning, the initial topology. Then we can define using this evaluation. So we can define E of f calculated at the point x to be equal to this value, where f is not a continuous function from on I. Why? So It is easy to verify, as I have already mentioned, answering the question. So here we can calculate that E bar star 1 of X. This is the unit element of algebra CYX. So a state evaluated at this function is 1. So from this, it easily follows that it is a projection. This is a projection, and of course it satisfies this bimodal property, and so it is an expectation of the desired form. So so conversely, if we have an expectation then we consider the following map. So first we can include X and in CX star. This is simply evaluation. Or in other words, we correspond to a point X, the delta measure concentrated at this point X being an element of the dual space. And also for this E, we can take the Banach dual map, which will map the dual to CX to the dual to of CY. So in fact, this composition is of this form. So the only thing which we understand, we need to understand that, is the following: that from the bimodule property of conditional expectation, it follows that the image of X is not somewhere in Ci of CY star, but is in S of CYX, as here, because it should be multiplying by some collection of functions, continuous functions on X, which approximate this delta function measure. We understand that it is concentrated in the fiber. Okay. So this is about property of being of a finite index. We will speak a little bit later. Okay.
I'm
So,
sorry, but why
now-
fiber should be finite? Is it
Yes,
necessary
yes,
for us?
yes. Yes,
It
yes.
should
This
be
is from the fiber is not only finite. They are uniformly bounded.
Okay.
So there is a number, some m, such that the number of points in each fiber is not more than m. So,
Okay, yeah, sense. Mhm.
so in these examples, so everywhere, so here it was, this m was 2, here this m was 3, and here once again this m was 3. Okay, so it is uniformly bounded.
Yeah, but it seems construction works for any fiber, right? Or because whatever you said here, it works for any fiber. I couldn't see why fiber must be finite,
Mm,
or maybe not. I don't know.
okay, so to me, it also seems that at least at this stage, it works in a more general situation. But mm, yes, I think you are right. So this construction works for not necessarily for finite fiber, but of course further steps need this property. Okay, thank you.
Yeah, thanks.
So now we pass to a sketch of proof of this theorem about metric spaces. So now consider a metric situation. As I have explained, this is the same thing as a second countable. In this case, the unit ball of the space of functionals is compact metrizable. Because it will be also it will be also so the unit ball is star-weakly compact, and also it will have a dense countable set in this case, and so it is second countable compact, so it will be metrizable. And the desired expectation will be constructed by Michael type selection theorem. Proved, this version was proved by Horvath I even will not formulate this theorem because we need a very specific case of it, simple case. And the general formulation needs a lot of additional concepts, definitions, and so on. So I wish to avoid this. So I wish to give some steps of construction, and then I will say that this is covered by the formulation, by this theorem by Horvath. So we wish we define a set-valued map. So Michael's selection theorem says that under some restrictions from a set-valued map, one can for set-valued map, one can find some set-valued map, and one can find the obvious one value map which is continuous, and at each point it lies in this set which were defined by a set-valued map. So this is more or less the setting, the general setting of Michael type theorems. So to apply it, we need to start from a set-valued map specific for our situation. And this map will be from X, of course, to Cy star, because a selection from it should be this our expectation in that interpretation which we have just explained. So this map will send each X to some Cx, which in fact will be situated in states of and this is as I have already explained, is inside of this Cy star. So first we split X into strata XY with the number of points with the cardinality of fiber exactly Y over this stratum. So for example here, for example here we will have stratum X1, and the remaining part will be X2. And for example here we will have X2 and the end point, and the remaining points will be X3. So there is no X1 strata here, and so on. So we introduce these sets, and also we will consider. So it is useful to consider the unions, and these sets, in contrast with XY, are closed. So the other strata, they are open inside the closed. So in fact they inherit. They don't inherit many good properties. And this is one of problems, maybe the main problem, which led to these difficulties. So difficulties with our proof, our old proof. Now consider connections. Or they were called gems. This is the following. These connections are between a point X, which lives in some strata Xi, a state from S C Y over this point, and Xj for some j which is more than I, such that our X is a limit point of points from Xj. So for example, if we consider this example, this point is from X1. Okay, so X1 we have a so these parts are X3, these are X2, and this limit point X1. And this limit, this point, if this is X, our X, it can be approximated by points both from X2, if we will take these points, and from X3, if we will take some intermediate points. Okay, and we in the same way we construct. So let this state be of the form so lambda 1 and so on, lambda I. So we have exactly I distinct points in the fiber. So we have functionals, delta functionals in these points, and we have take their convex linear combination, some specific. And then so we have y over x is y1 and so on, yi. And then we have multiplicities which with which the points over a set which approximates this point remaining in xj give rise to multiplicities. So we have multiplicities m1 and so on, mi. So this means how many points of the elder stratum goes to 1, to y1, and so on to yi. So for example, so when approach here, so here we have multiplicity 1 and here we have multiplicity 2. So then we can construct the new so this will be splitting of this element and so on. And for the last, we will have okay, so this will be once again a convex linear combination of delta states of points, delta states corresponding to points over. Now we have with these multiplicities, we have so the multiplicity, so cardinality of the fiber. So okay, so J is equal to M1 plus and so on plus Mi. So we define this this state and this is defined over all points of this stratum xj. So this is this connection. Now we start from uniform from a uniform state over the first non-trivial xy, as it was in the example, one of examples, x1, for example, may not exist, and only x2 was there. So we can see the first non-trivial, and so there, C, which this will be simply the singleton. It consists only only of one state at each point. And then we go to elder strata, always adding these elements which arise in this form, and then consider so we obtain step by step some states over next strata, and of course and take their convex whole. So we need to understand the following, that we have only finitely many types of connection. Okay, so because at each step, for example, each can be split in 2 parts or in 3 parts, and so on. Anyway, we have only finitely many combinations. So we obtain finitely many ways how we construct this, how we perform this passage. So as the result of this observation, we can say that in fact we obtain this. So this will be our C over point X, this set. So in fact it will be not so this is the entire state space of several of, say, for example, of 3 points. This triangle is but we see that at the first step we had only as the singleton, so this is the middle point. At the next steps, of course, we obtained a worse situation, but nevertheless, it was something. This was something. We obtained something like this. So it is. It doesn't come. That doesn't approach to the border. So in fact, this means that if this is more or less some delta, then if we will construct from this a conditional expectation, then it will be of finite index k, which is more or less 1 over delta for the minimal delta. Okay, so values will be greater than some small number. We obtained this. If we the dimension of the cardinality of fibers was around not more than m, then delta is less than something like this. So we need to verify, to apply Michael theorem, or this version. We need to verify that this set function is lower semi-continuous. This means that for any x in X and any open C in Y star, open V in C Y star, such that it intersects with Cx, the set U formed by those X prime such that Cx prime intersected with V is not empty, this set should be open. So taking some specific x, we need to verify the following, that if we have a net convergent net with goes to x, so we verify semi-continuity with respect to not to the, this metrizable part, but the entire COI stars. So so we need to speak about nets, not sequences. We need to verify that starting some point, some member of this net, we have Cx lambda entering this set V. But this is in fact evident according to our definition, our construction, because this V is defined by some finite system of functions. So this we have some functions and some centers, and phi sits in V if and only if we have this estimation. But by the construction of our extensions, we see that for each specific function, say f, the values of this this state regarded as an element of the entire dual space C of y star goes to the values of this to the value of this state on fixed function f. They are constructed just for this purpose, just for fulfillment of this property. So this is follows from the construction. So we can apply this theorem. Can apply this Horvat's theorem. So generally, the initial Michael theorem works for metric space X and for metrizable Banach space of values. But this modification, this development of this theorem requires only metrization of that part of a local convex space where these convex sets are situated. And this is the unit ball in the dual space, which is in our case metrizable, as we have explained. So we can apply this property, and this more or less completes the sketch of the proof of this theory. Now we pass to the to the counterexample. This counterexample is in fact is in fact a well-known in the field counterexample to Michael's theorem. Due to Megel. It is nicely presented in the book of Repovsh and Semyonov. So the construction is the following. So I think I will, so let's see how much I will manage to present. Okay, so Z is a Hausdorff compact. Then we can consider Zn. This is subsets of Z of cardinality less or equal to n. In the example itself, we will have n equal to 3. So we have a map from Zn to this Zn in square brackets. So if we have an element of this Cartesian product, it is sent to the set. So for example, if we have A, B, A, it is sent to A, B. And the A, B, B as well is sent to this element. And so on. So in this case, n is 3. So so topology is this space is equipped with the quotient topology, which also is called Vietoris topology. Vietoris topology. Now what I wish to say that we will consider the space which we will denote that included, and it is a subspace in the Cartesian product of Z and that Zn. So it is formed by couples here such that Z is an element of X. Z an element of X. And we have the second projection. We have here the second projection onto Zn in square brackets. And so this is a statement. And this is a branched covering. Okay. So in fact, so over a set X, Y, for example, we have fiber consisting of X and Y, and so on. So this is, in some sense, the tautological bundle, the tautological fibration. So, maybe if I will have some time at the end, I will explain why this is really a branched covering. So why the map is open. So the cardinality of fiber is evidently bounded by n, but the other properties are not so. Why they are compact Hausdorff and so on. So at this moment, I will leave this and go further. So now the example. The example is the following, more specifically. Now let n be equal to 3, and z is the one point or Alexandrov compactification of an uncountable discrete set space gamma. Then we have this our branched covering. Branched covering in this specific case, and as above, this map Z to delta Z is an embedding of our space Z into the locally convex topological space C of Z star. C of Z star. And we can define one can define the lower semi-continuous set map from X, where sits Z. So I write triple, but in fact they can coincide. So two of them coincide. Then this notation means, so if we have A, B, this means the set AB, of course. So, but this allows us to to write always three items. Okay, and we send it to this CZ being the convex hull of delta ZE. And this is of course the state space of C pi minus 1 of Z. So it doesn't have a continuous selection by this theorem of Meger. So I will now give a precise formulation. So if alpha of gamma is 1 point, so maybe as above. So this is, so we have a discrete uncountable space and 1 point compactification of this space, okay? And gamma is embedded in a locally convex vector space Y, vector space Y. X is alpha of gamma 3, and the F X Y. So this will be F. Sends to convex hull. Then F is lower semi-continuous. With compact convex values, which doesn't admit a continuous selection. So, but a continuous selection of this map is just a desired conditional expectation. So in this way, we have proved that there is no conditional expectation at all, even without the restriction to have a finite index. So even without finite index, there is no conditional expectations here, okay? So I have 5 minutes more, or 7. Then if I have a little bit more time I wish to say several words about why this idea of the proof. It's also very interesting and beautiful. Of the proof of this Megel theorem. So that it is locally semi-continuous, this is an easy exercise. But more interesting, why it doesn't have a continuous selection. So suppose the contrary, that there exists f being a continuous selection. Then denote by W the non discrete point of X. Then for first for 2-point sets, so X is some beta and our non-discrete point W, which sits in alpha gamma. So X is in X, 2-point set. So the value f of X must be epsilon close for arbitrary epsilon. Take arbitrary epsilon, and then it should be epsilon close to the middle point of the closed interval BW, which is for simplicity, I use this notation. Delta functional I denote by the same notation as the point itself. For some uncountable set gamma prime in gamma, then we pass and all beta in this gamma prime. Then we pass for 3-point sets. Which sit in this 1-point compactification of this set, and apply the previous consideration for medians. For medians of the triangle. So, and then we understand that the value f of X should be close to the middle point of medians, these two medians. So this is and the other is No. But this is the middle point of this median, and this is the middle point of this median. And for sufficiently small epsilon, they can be close simultaneously to these two distinct points. The point of intersection of medians is not the middle point of each median. So, and the remaining minute, at the first glance, it is not understandable why this doesn't work, why it works for uncountable set, and why it doesn't work for a countable set. But the point is to calculate these relations, to obtain that it is a middle point of this, we need to take, say, for example, if we have approach somewhere, we need to consider a function, say, which is 1 over this approaching part and less than 1 of the remaining part. So this will be function f, and then we will take f in power y, for power y. Then we will have countably many conditions at which we need to verify convergence. And for each condition from this set, we should exclude finitely many points to obtain epsilon closedness. So we have countably many conditions, and for each we exclude finitely many points. So totally we have to exclude not more than countable number of points. And then uncountably many points remain. So that's why it is the argument is applicable only in the case of uncountable sets. So it sits here. It sits here. So I was speaking fastly, and it was not clear. So thank you for your attention. I will stop at this moment, and I will use this opportunity to send my congratulations to ladies in the audience with the tomorrow holiday. All the best to you.
Very nice.
Okay.
Thank you. Thank you for the talk. Questions, please.
Yes, I have a question in your construction of the set-valued functions using the convex combinations of deltas,
Yes.
using multiplicity. You have written so long convex sum, but it's supposed to be a set, right? Not just single. Because
Yes,
whatever you're
yes.
written, you add them up all.
For each so this was we considered an element. We considered here.
Yes, this one.
We considered an element. Okay, so of this form. Then we considered some approximation from elder strata, elder stratum, the one stratum, and constructed this thing. Okay.
Yeah.
And then, or maybe And then we were taking the convex hull of these elements.
All these elements.
All
Yeah.
these elements. So, of course,
I
the
see.
taking of convex hull commutes. So we can take the convex hull of some elements at the previous stage, and then this is the same thing as convex hull of the corresponding members and the over elder strata. Okay.
I see.
So
Okay.
we obtain some convex set inside
Okay.
of this simplex, which describes all states, and it is strictly inside because of finitely many steps. So each time we divide by some, so for example 2 or 3, which was dividing, yes. So some number which is less than the number of these points. That's why we obtain this estimation. So we have a distance from the border. So this is not a conditional expectation which has a kernel, but contrary, it's a conditional expectation of finite index.
Okay.
Thank you.
Okay. One more below. Whenever you said lower semi-continuity, you said you have to prove that for every open set, which is with the sections non-empty, inverse should be open, right? Yeah, right here. Did you mean open or closed? Because you start with the net. You took the net conversion to X and you proved that X again must be something like that, right?
Open. This is for open sets, and I use in a very serious way that this is the description of open set in that locally convex space of functionals.
Yes. But what about U? U should be open or closed.
You should be open.
So, but you took the net which converged to X, and then probably you pried X net from U and limit also from U, right?
So I mean,
maybe I missed something.
I mean that close points to X. What are the close points to X? That are, we consider any net and the points starting some place. These are neighboring points to X.
And this, okay,
and all these neighboring points satisfy this condition. So it is an open set.
Okay, I got it, yeah.
Okay, maybe not very precisely it was told, but the idea. Okay, so open.
Yeah.
So I was trying to explain that close points close to X satisfy this condition, so it is open.
Okay, and final question, you promised to say something in non-commutative case. Do you have an idea how to quantize all the stuff in there for non-commutative sister algebras?
So yes, so the definition is that non-commutative branch covering is such a pair algebra and subalgebra such that there exists a conditional expectation of finite index.
Okay.
But unfortunately, it works at this moment for metric spaces and also some other spaces. So also for some other spaces of this class, but with very specific properties. So but in this case, we don't speak about some specific branched covering. We speak about the space and these properties. But of course, to cover these bad topologically situations, we need to put some conditions on specific branched covering. So this will be the solution in general case. So also I wish to say that it is a little bit surprising that obstructions, so this problem which arises, is outside metric spaces. So it is of general topological nature, not of algebraic topological nature, not some abstractions to, so this is a little bit surprising. This is a little bit surprising.
Yeah. Okay. By the way, your definition of expectation that you said in the beginning of your talk using discontinuous function, so it was wrong, right? Or does it work, or it just was? In the beginning, you said you can use some summation with respect to some discontinuous function psi. Yeah, this one.
Yes, in these cases,
this
is exactly that thing that gives the selection, that proof with selection, Michael selection theorem. So to each point, we have two combinations of two. So this is a section. So we take one element. This is a selection of some set valued map. So this is already the answer.
Yeah, yeah. So
Which
your
gives,
psi is specific, right? You have very special psi.
Here examples of course are very simple. Examples of course are very simple. Here.
Okay. Yeah, thanks. Yeah.
Thank you.
Sorry for any questions.
Oh, it's a pleasure.
Thank you.
More questions, please. Well, if there are no more questions, then we thank the speaker again. Thank you very much.
Thank you.
Thanks a lot.
Okay, see you next Friday.
Huh?
See you next Friday.
Yeah. Thanks again.
Thanks.
Bye.
До свидания.
До
До
свидания.
свидания.
До свидания.
До свидания.
Да, всех
До свидания. Bye.
До свидания.
дам
Рад
вас
был
с
всех
наступающим
увидеть.
До
праздником.
свидания.
Ух.